Alright, so as you can see, my title was made up 2 days ago, that's why it's on the program, so my apologies. I've been asked to speak about soil moisture. Soil moisture is exactly from the retrieval side. It's more soil moisture in terms of the calibration, validation campaigns, and also about scaling in soil moisture remote sensing. So in the global context, soil moisture has a vast importance because it's driving the fluxes between the land surface and the atmosphere. It can inject a lot of water into the atmosphere. Well, this image here is a bit, I'm cheating because those are lakes, but it shows more graphically the effect that the soil moisture can have when you have a large gradient between the two. So it affects the weather and the climate, of course, as well. In the same instance, agriculture has a vast need for knowledge of soil moisture. Without soil moisture, you can't grow anything. Without soil moisture, or knowledge about soil moisture, about the dynamics, the farmers would have issues with their planning. Now, most farmers know intuitively what the dynamics are, what the years for the fields, but we could provide a much better information. So soil moisture is also important when you come to higher resolution issues. So for example, flooding. If you know how wet your soil is, your flood forecasting models can predict much better the amount of water coming down the rivers, because if the soil is saturated, nothing will infiltrate into the soil, it will run off into the river systems. The image that you can see here is Brisbane in 2011, when it was totally flooded. So my colleagues who had just started with the European soil moisture campaign had sent me images 2 days before saying, well, you've got a big front coming into the east coast, look how wet the soil is already in the area. They'll be getting wet feet. Here you go, they were right. Unfortunately, the BOM was not looking into soil moisture from remote sensing at the time, so maybe there was a little bit of a underestimation. And soil moisture is also important for bushfire applications. So if we know that it's been dry, that the plants can't take up all that much water because there hasn't been any much water in the soil, fire potential is much higher. Similarly, for the understory, for the leaves on the ground, there's a relationship with the soil moisture. So if we can measure the soil moisture, we should be able to predict also bushfire events, or the risk for bushfire events, much better. And something we've done I started here at Monash with an undergraduate student, but then that we implemented in Spain was to look into the relationship of land surface temperature and soil moisture. And then we picked all the fire events in Spain, and we looked at the dimensions, at the extent of the eventual fire. And while you've got the land surface temperature on horizontal and the soil moisture on vertical, you can see, yes, you've got some fires. Well, the issue in Spain is there's some deliberate fires for clearing, and then it's accidental, and then you can use it for building houses on it. But you can see all the big fires here, the red ones over 500 hectares for Spain, this is big. They're all down here when it's warm and dry. There are not many fires actually when it's warm and wet. So there's a relationship, and we built a forecasting system for Spain at 1 kilometer resolution that works reasonably well. So if on a historical basis, we can predict 80% of the fire extents. So we have a lot of misses and false predictions, but if there's a fire, we are actually fairly well placed to predict how big the fire will become, just because we've included the soil moisture. So there's a lot of information in the soil moisture product. It can help a lot of applications. The problem is soil moisture is very defined in a way. If you talk to different people, they come up with a different definition. So in general, soil moisture is the water in the meadow zone, so in the unsaturated zone, because anything below that is groundwater, is saturated, it's not soil moisture. So it's not necessarily only the water in the soil, it's usually referred to for the unsaturated zone, but how deep is that one? It's very. Okay. So another problem with the definition is that soil moisture can be defined between absolutely dry and saturated. And in between, you've got the wilting point and the field capacity as well. And I'll be coming back to that later on again, where I'll point out some of the miscommunication between the remote sensing community and the modeling community. So bear that in mind, all right? So there are lots of different ways of defining soil moisture. Soil moisture can be modeled, not only remotely sensed. So we can have physically based modeling, so with Richard's equation we can properly model the diffusive process of water entering the soil and propagating vertically through the soil. Fair enough, we can do that. There are also more simple models that only look into how much water is in the entire catchment, and then they say, oh well, I've got a 10 centimeter layer on top that dries and wets up and then pulls up water from the bottom, from further down, or puts water down, so it's the catchment deficit. So how much water I can put in the entire catchment to fill it up. Others look into discrete layers. Jules, it's been used by the BOM, Isabelle by Météo France. VIC is a more global one developed in the US by people in Princeton and University of Washington. They all have layers, and then there's a process of water transmission between the layers. And the layers have different thicknesses. And then there are very simple approaches as well. You can model soil moisture by just using precipitation through assuming decay rate of the previous day's soil moisture. So this is the antecedent precipitation index, for example, where you just add a factor of k, which needs to be smaller than 1, to increase what the memory is from the previous day. And then when it rains, you just add how many millimeters of rain. So it works reasonably well if the k parameter has been calibrated to the locations. But it only shows you the surface. It doesn't give you any information about what's deeper down. Indeed. But there are ways where you can propagate the information from the surface deeper down. So you have sort of a profile information. You can get the dynamics. So you can see modeling can give you a fairly varying range of approaches, but they all need calibration, they all need in situ information to actually build the models and inform the models properly. Most of the time you don't have much information about the soil to start with. So how can soil moisture actually be monitored rather than modeled? So there are various ways apart from models. So this is, I stole that from the UN. This is from the Australian Landscape Water Balance Model, let's call it, yeah, close. And you can get the data. So it's based, I think it's on Joules, or NEM, or AOR, or yeah. So, well, it's a water balance model. Takes into includes various input data. You can also measure soil moisture in situ. So you can put sensors in the ground like those ones, they're capacitance probes, they go down to a meter or something, and you can measure it every 10 centimeters. But this is only basically a point. You measure it within 10 centimeters of the sensor. You don't know what's happening 1 meter, 10 meters, 20 meters, or a kilometer away. You can also use cosmic rays, moisture. So the reflection of cosmic rays, they're being changed when they hit the surface, and as a function of how wet they are, the reflected neutrons have a different state you can measure, and then you can relate that to soil moisture. It has a bigger footprint of about 600 meters, and it gives you a bit more depth than the methodologies I'll show you in a minute. So this one is a stationary one. You can also put that on a car and drive around the area and try to map the soil moisture spatially through that one. That's a research project that we've done in the past with Cyber. But you can also use satellites. So this is where I'm going to get into my actual talk that I was asked to give. It's the use of satellites to monitor globally or continental scale soil moisture. So throughout the day, you've heard about various technologies and so on in measuring land surface conditions. There's of course the optical sensors, you've got thermal sensors, infrared. There's a whole range. You've got SAR technologies. I think there was a talk this morning on SAR. You can also have LiDARs and all these things. So they measure different states of the surface, while the optical sensors are more related to the colors or really the skin of the land surface, With microwave sensors, you can look deeper down. Right? And that's why we are actually using mainly microwave sensors to measure soil moisture. Basically because given as a function of the frequency of the microwave sensors, you get different sensitivities to the soil moisture. And the lower the frequency, the more sensitive it is to the soil moisture. The higher the frequency, the more issues you have also with vegetation on the surface, but also the smaller your observation depth. And when I'm talking about us measuring soil moisture, it's actually at 1.4 gigahertz, that's about 21 centimeters wavelength, you measure anything between 1/4 and 1/10 into the soil. So between 2 and 5 centimeters. That's how much you're measuring actually with microwave technologies. Okay? So that shows you that there's a bit of a discrepancy between what is actually soil moisture. That's why I was mentioning that earlier on. There are also different technologies in the microwave. So any object emits energy in the microwave spectrum. The benches here, you, the soil, the buildings, everything. There's microwave radiation everywhere in the background. And that can be measured. That's called passive microwave remote sensing. So you're just measuring what's naturally emitted from any surface. You can also send a signal to the lens surface and look what's bouncing back. Our vision works the same. Light hits the surface, reflects back into our eyes, and we see something. That's also that's active remote sensing technique. So when you send a microwave signal, the advantage is when it's active is you can focus on a smaller point. The natural emission, background emission of microwaves is so low, you need to collect data basically from a large area with the current technology. So at the moment, the biggest antenna that we have up there in space is 6 meters. That means the footprint is roughly 40 kilometers to get a sensible information out. Whereas if you send an active signal, you get about 10-meter resolution with the same dish. There have been, since 1978, at the end of 1978, with an American Navy satellite, there have been continuous microwave missions up in space. So the ones up here, they're passive, they're just measuring the emissions, as I said, and those ones down here are active missions. You can see the Europeans have been actively launching a lot of high-resolution satellites, but the whole family of the Sentinels is actually going to be a satellite family of about 18 satellites. There are also other technologies out there that are called scatterometers. They're also active, but because of the technology, they're actually also measuring tens of kilometers. However, with the SAR, with the radars, you get really to the tens of meters. All those missions have resolutions of in the order of 30 to 70 kilometers. Now, for lens surface applications like flooding, agriculture, that doesn't make sense. And I'll get back to that in a minute as well. So when you compare active and passive microwave and remote sensing, you see a totally different image. So on the left-hand side, you see a passive microwave image of the same area. And on the right-hand side, you see the same from an active satellite. 1 kilometer resolution, this is 25 kilometer resolution. By the way, this is Lake Eyre. Simpson Desert. This is the the Stormy Desert over here. You can really see the structures with the active satellite. Lake Eyre looks like a blob here, whereas you see quite a bit of structure with the radar. Disadvantage of the radar is actually you see a lot of noise. So this image here is a stack of images, so that I'm reducing the noise. It's not a one-off image. But we still see a much better structure, even with a single image. So the problem is when you send and launch a new satellite on new technology is you don't know how it's going to respond to the measurements. You don't really know what to expect. You have an idea, but you don't know until you've taken the first measurements. So that's why we do calibration and validation campaigns all over the world for those satellites. Because also that the sensor technology has been developed in a lab or on an A-frame in a field. So it only looks at a single homogeneous point, whereas, as you can imagine, when you measure 40 kilometers in the footprint, it's not homogeneous anymore. So you need to figure out what's happening underneath. And that's why we do the validation. All right. So we are looking into how does the calibrated sensor actually see heterogeneous areas? How can we adjust our retrieval algorithms to match what we're seeing on that surface? So for that purpose, one of my first campaigns was going out to the Australian arid zone around Lake Eyre, Simpson Desert. We spent a few weeks out here taking measurements. We flew over Lake Eyre, we flew over the Simpson Desert, and over areas. So we flew means we had an instrument on an aircraft, whereas I was walking on the ground at 50 degrees. One day it was 54 on Lake Eyre, so it was reasonably warm. So the advantage of going out there is it's flat, it's dry, there's no vegetation, so it's a beautiful place to check your algorithms. It's actually, I love going out there. It's amazing. The heat is a bit of a downer. But then we saw with you can see here vaguely the data that we collected in here. It had rained a few months earlier, we saw the water, and over Lake Eyre it's also wet. So we see the contrast with the aircraft instruments. So that was good. Sensor on the aircraft works, and we see what we're meant to be seeing. So come on satellite, tell us what you're giving us. The problem was that we chose Lake Eyre because salt lakes are assumed to be fairly homogeneous on a large scale. You don't expect it to be wet, dry, with stuff like here and there. You think it's 50 kilometers of just flat, salty surface. Now, when I was walking out there, and you'll see some photos in a minute, that wasn't the case. And also, when we looked at this airborne data, you can see vast differences in the measurements. So this is the area of a single footprint of a passive microwave sensor. And you can see here, very warm in the microwave spectrum areas and very cool ones. Cool means there's plenty of water, or there's a high dielectric constant, low dielectric constant, sorry, which means there's a lot of salt potential. And in that case, it was actually, when I was walking out there, it meant that there was not only salt, there was also water, and this is the day when it was 54 degrees. I walked 2 kilometers straight into Lake Eyre. Those were my footprints 2 days later, when I came back and retrieved my instruments. The water had evaporated from the footprints, the water was just under the surface. It evaporated and was left, what was left were blocks of salt in the shape of my feet, of my boots. That shows you how much salt is actually just under the surface. Now, that also meant we had to discard Lake Eyre as a reference because it was too heterogeneous. So you see, for the calibration campaigns, you have this idea, you drive 2,500 kilometers one way, and then it doesn't work. So we focused on the Simpson Desert, which was much more homogeneous in that sense, and apart from the rain on the last day when we had to evacuate everyone at 2 a.m. in the morning to get out of the desert. In the rain, driving over dunes was not that nice, and we were the last ones to make it out of the desert. Everyone else who was behind us was stuck for 2 weeks. They couldn't get out anymore, they had to be supplied by helicopters. So, for those who usually spend their time at computers, we do a lot of work to get data to you, and we suffer a lot. A bit closer, we did a campaign in southern New South Wales in the Murrumbidgee River catchment where we covered the entire catchment. So basically you can see here, this is Murrumbidgee, Canberra is here, Hay, if that says anything to you, is over here, Balranald here. You can see actually here, Canberra, there's the lake, and we found some weird features around Canberra that government agencies were never really forthcoming explaining to us what that was. So there was 50,000 square kilometers. Each of these blocks is 100 by 50 kilometers. So it's 2 satellite footprints essentially. So we took a lot of measurements there. We sent 30 people every day walking 5 kilometers here and back. We had stations, we sampled vegetation just to get an idea of how accurate the retrieval by the day algorithm for the soil moisture was. We had plenty of rain. That was actually the weekend when Cameroon got fairly flooded, so we had 118 millimeters over the weekend. That was in 2010, February 2010, at the end of the drought. So you can still see extremely dry here. And then it started raining, which was great for us to see the contrast. So when you look then into the satellite product, and this is a downscale, sort of downscale, this is resampled product from the satellites, you can see the same structure. You see the national forest here, the national park with the forest here, and you see the same responses in the satellite images. So from that perspective, it was really good. We saw the spatial patterns correctly. So that was great. Now, that was the pure calibration and validation. I'm not going into calibrating the retrieval algorithm as such. I want to talk more about scaling issues in soil moisture Earth observation data. As I said before, when you take the passive sensors, they're much more accurate in terms of the soil moisture value they're giving, but they don't have the spatial resolution. Whereas the active sensors can give you the spatial resolution, but they are very noisy and they don't give you much of an idea of how accurate they are, how well you're actually measuring soil moisture. It gives you a rough idea, but not really well. So coming back to that one is, people start merging those, including me, merging those two. You get the spatial information from the radar, and you get the accuracy from the passive, and then you try to figure it out. What you can also see here is, I forgot, here you've got the footprint of one of the American satellites, and you see all the heterogeneity, forests, fields, water areas, actually there are a couple of lakes somewhere around. So this is 36 kilometers here, this extent. And this would be the final product of the passive sensor. So, and that raises a question, how do you actually report on soil moisture if you have a passive sensor and you have one value for the pixel? How accurate is that value? Now, when you're hearing people talking about, oh yeah, we're getting small sense map, low resolution accuracy of 0.04 volumetric percent. For an image like this, it doesn't make sense. Because when you go and you look at the distribution of the soil moisture within it, you can have a vast range of soil moisture. Okay. We're talking, when we're talking about passive product being 0.04, and it's 0.04 from the mean response of that image. So that means it's this range, basically. What's happening to all those areas? They're not being represented as such. Doesn't mean that we're doing the wrong thing, it's just translating the information into something that can be used, especially for people who are doing land surface modeling at various scales and then taking the low resolution footprint. They need to understand what it actually means when we're talking about it and we say we've got this one value and we've got an accuracy of 0.04. So, but for us it means if the soil moisture retrieval algorithm is here, we are within the range of the target. So for us, the validation is okay. It's good. The algorithm works as it should be. But as I said, for somebody who's doing high resolution modeling, that's not the case. Now, spatial downscaling means, as I mentioned before, that you're taking the coarse resolution and you get a better product. Again, Marubiji, and I've downscaled this area. So here, this is the original high resolution from the aircraft, and this is the downscale. There are some differences you can actually see. That's okay. I can take it. What you can see is you see some structures in the differences. So this was a waterlogged area, and this is actually the Marubiji River catchment. The other areas we were able to reasonably well retrieve. And the important thing is also we are not improving, or we're not destroying the 0.04 accuracy. We are maintaining that in the error bands. what we are doing is, here you can see the comparison of the low resolution with the soil moisture network in situ, and the final product, again, against the surface soil moisture network that we have out there. The bias or the error is roughly the same, but the relationship is much better. So this is the important thing. Alright, so as I said, you're maintaining the error budget, but you're getting a better relationship with the high resolution data. Now, coming back to how to report on soil moisture, and to the figure that I've shown you before. So you've got soil moisture is water in the soil. So you've got anything from very dry to saturated. All right, so technically you could say 0 to 40% of the volume. So if you have a porosity of 40%, 60% is taken up of the entire soil volume by the soil particles, and there's 40% void space. So we can say 0 to 40 is the range. Or in soil wetness terms, 0 to 1, because when you talk about soil wetness, it's a scaled product from maximum to minimum. Problem is with the model in dynamic range, it's usually wilting point to saturation, or in some models, wilting point to field capacity. All right. So if you're getting a data product from the satellite community and they're saying it's a soil wetness index, you really need to look into the manual how they define that range here. Right. And then adapt it accordingly. Because with the sensors you can see below the wilting point, but most models stop at the wilting point, which is an arbitrary value to start with. So it can add a few issues when you're not careful with that one. It's all about using the right language, because as I said earlier on, the remote sensing community and the modeling community don't they use the same words but mean something different. If on one of the two sides there's someone who doesn't understand the difference, then there's a conflict. And also in terms of,
just on that point about the wilting point, can the satellite product point out when it's reached the wilting point, even though it can show further? Can it just highlight that we're at the wilting point now?
You have to do some tweaking and some interpretation of the time series.
Yeah, right.
So it's not, the image can't tell you. You have to do a time series analysis.
Yeah. Okay.
And then even then I would be very, very doubtful, because different plant types have different wilting points with the same soil. So actually what they're doing with the modeling is, the wilting point is at 10%, right, but not for the plant.
Wilting point is a soil corrector or vegetation corrector?
It's a vegetation, it's a function of the vegetation. Because some plants can extract water from drier soils than others. Right. So in terms of the depth as well, so most models give you top 10 centimeters. Okay, but what we are measuring, as I said, is somewhere between 2 and 5 centimeters if you're lucky. It varies. When it's very, very wet, even the 1.4 gigahertz is only the top surface. Sorry.
But given the clay soil and sandy soil, cold water, there's different suction.
Yeah, well, wilting point changes with the soil, but also with the vegetation.
Okay.
So you need to be careful when you're getting soil moisture products, whether it's absolute soil moisture, whether it's a normalized or standard soil moisture product, whether it's temporal anomalies. So when we're doing a lot of validation, we're looking at temporal anomalies to get the noise out, because the in-situ sensors that we're using for validation actually show us also something different. So what we are more interested in is whether our relative change to an average is the same as the in-situ sensor shows us over a 5-week window centered measurement. So that also comes down to when you're doing validation is, okay, here are a number of satellite products plus a land surface mode product from NASA. And this is our reference station network. All right, so you can see they all have this fairly similar correlation coefficient, but their standard deviation is very different. So Aqua is a passive active mission, but with a very low resolution, has a lot of variability in the retrieved product, whereas this one here is a Japanese sensor, and it doesn't show the retrieved so much, it doesn't show much variability. But they all have this nice the interannual variability through seasons. So that's why they all have the same correlation. However, when you take the anomalies and you look at the anomalies, the order of how well they do changes, and also the standard deviation becomes suddenly fairly equally distributed, but the correlation is suddenly not the same anymore. That means the sensors actually see different relative changes. And that is because they see different depths. Because they have different technologies, different frequencies. So, as I said, I'm not saying the solar moisture products from space are bad. I'm just saying you need to know what you're looking at. And for the climate community, I've put that one in. So that's a Hofmöller diagram of the different satellites in the model. So Hofmöller diagram here means x-axis is time. And I've taken half-a-degree slices of Australia and averaged each half-degree slice in the latitude. Right? So basically what you see here, those stripes, that's Tasmania. But what you see here is also wet every 6 months. In the north it's wet in summer. That's when it's dry here. It's wet in winter, whereas it's dry in winter in the north. So we see the right thing. And those products are all scaled, so it's all normalized products. And I'm looking at the anomalies, and the model is telling us it's wet in the desert. Right. Well, which one is right, which one is not? Are the satellite products that are consistent showing us the right thing, or is the model right? Given that we don't have measurements out there, can't say for sure, but I will trust the satellites in that case. But also over here you can see that the different satellite technologies have different advantages in different terrains. Some are better in the desert, some are better when there's vegetation. So it's not that one single product is better than the other. You have to think about which one you're using. Right. So as a conclusion, after talking about solar moisture, it's a key variable and we can measure it to some extent, but you still have to understand when you're using it what it's actually all about. We've done a lot of calibration, validation campaigns out there so that they represent what we're expecting, but it's only snapshots in time in space. So the users really need to understand both models and satellites when they want to use both. They want to get the best information out of it. And there are many upcoming opportunities. And the Europeans are launching a whole suite of satellites, free data access. There will be a lot of companies that will be trying to sell products, which may not be reasonably well-developed products, just pushing out products. So the better you know what you're expecting, the better you understand what is being measured, the better you are analyzing the accuracy of those products. So with that, that's my last slide.